All right, this is the last section to our review for Chapter 2 test, or the second test. Keep in mind that if you see a problem on the review, there will be a problem almost identical to it on the test. Know the problems on the review, you're going to know the problems on the test. Here's the last 7 problems. Number 16, find the solution to the polynomial inequality. Express your solution in interval notation. One thing I want to remind you of is that solving an inequality follows the same initial steps as solving a polynomial equation. Step 1, set to 0. It's already set to 0, so step number 1 is done. Step number 2, factor the polynomial if possible. The left side is already factored. Thank you very much, Mr. Hawks. That's done also. Step 3 is the same as well. Set each factor equal to 0 and solve. Now you should know that this page, one identical to it, is already posted in your Quickly content under Blackboard, so these problems are worked out. This video is just to show you how they are worked out. Set each factor equal to 0 and solve. Easy here. X is 0. X plus 3 is 0, or x minus 3 is 0. Solving these guys is no problem. So I have 3 values. These are what are known as my critical values. They are the ones I'm going to use to mark the number line and test my intervals, which is step number 4. Mark the number line and pick a point in an interval to test it. So you're going to test your intervals. So I have -3, 0, and 3. And you remember the concept. Everything in these intervals, these parts of the number line, everything works or nothing works. So what we're going to do is pick some values and test them. So let's test something in this rightmost interval. Let's test 4. What that means when I test 4 is I substitute 4 for x and see if I get a true statement. So 4 plus 3, 4 minus 3. I'm wondering if that product is less than or equal to 0. I don't know, let's find out. That's 4 times 7 times 1, less than or equal to 0. No. 28 is less than or equal to 0. Nope. So that tells me that this interval, this part of the number line, fails. It is not a solution to my inequality. All right, test something else. Let's test something in this interval. Let's test 1. That means everywhere there's an x, I'm going to put a 1. 1 plus 3, 1 minus 3. I'm wondering, is that less than or equal to 0? I don't know. Let's find out. 1 times 4. 1 minus 3 is -2. Is that going to be less than or equal to 0? I think it is. 4 times -2, which is -8. Yes, that is less than or equal to 0. So this value is good, which means this whole segment is part of my solution set. So I'm going to mark the whole section, the whole interval. Now you probably remember this shortcut. If you have simple factors like this, you can alternate yes, no, yes, no, yes So this is going to go just like this to save yourself a little bit of time. The one time you have to be concerned is if you see an x squared in here. If there's an x squared in here, you're going to have to test every segment. But since there's no x squared, I can test every other segment, and yeah, these two guys show a pattern. No, yes, no, yes. So here's my solution set. These two intervals right here. I need some ending markers. Since I have a less than or equal to, I'm going to be putting brackets. So my solution set is from negative infinity to negative 3, bracket, together with, we use the union symbol for that, from 0 to 3 with brackets. So that is my solution set. All right, let's go on to the next one, number 17. It says, consider this function, r of x equals x plus 1, x plus 2, x minus 1, 3 minus x. Find the x-intercepts, it asks. Remember, x-intercepts, to find an x-intercept, I let y equal to 0 and solve. Yeah, well, I don't see a y. Once again, we're reminded that r of x is the same as y. So in the place of this y, I'm going to put 0. Hey, this is exactly like solving a polynomial equation. Notice I've set it equal to 0. I have factored the thing. It was already factored, but I've factored the thing. My third step is to set each factor equal to 0 and solve. So x plus 1 is 0, x plus 2 is 0, x minus 1 is 0, so forth. Solving, x is negative 1, x is negative 2, x is positive 1, and moving the negative x to the other side and making it x, I get x is 3. So I have these 4 values that are my x-intercepts. Now the next question I'm going to be asked deals with the graph of this thing. Now if the graph of this particular function has these x-intercepts, negative 1, negative 2, positive 1, and positive 3, the only 2 possibilities for what this curve could look like is either this. Remember, it has to cut the x-axis at these points. It can look like that, or it can start low and go high. That's the only way a curve can go through these 4 points, this or this. Now my second part of my, after I've found my x-intercepts, which by the way are right here, after I've found my x-intercepts, the question is going to ask me to identify the graph. Which one is it? I don't know. Both of these graphs have these values as x-intercepts. So how am I going to find out if it's ending to the right going up, or if it's ending to the right going down? Well, I'm simply going to pick a point. Let's say 4. I'm going to pick a point and see if my y value is very big or if my y value is very small. So in the place of r of x, I'm going to put r of 4. And see what 4 does. I could pick any number. I could pick 5, 6, 7, but I'm just going to make it easy on myself. And I'm wondering about this, guys. Is this going to be a really big number or a really small number? Let's find out. That's 5 times 6 times 3 times, aha, -1. This is going to be a very large negative number. I don't even have to worry about what it is. It's negative. So this tells me that this is the picture of my graph, because at 4 I get a very large negative number. All right, so you're asked two things. Find the x-intercepts, that y equals 0, and solve. Secondly, what does the graph look like? You're going to have to decide, does this part go down or up? It goes down. And I believe on the Hawk's answer, you find a segment and you highlight it. Either it's up or down. Either it's up or down. So highlight the section, and once you figure out what it looks like, and basically by making your choice, you draw a picture of the graph. That's number 17. All right, you may recall that on section 6.1, I told you not to worry about section 6.1, the section on asymptotes. There will be a problem. I asked it to be switched out, but they said no thank you. So there will be an asymptote problem. Don't worry about it. What I'm going to do is figure into the final evaluation of the test, and this will not count against you. Hey, if you know how to work asymptote problems and you want to guess or you want to try, help yourself. It can count as a plus for you, a bonus, but bottom line, it will not count against you. You can get everything right and miss this problem and still make 100. All right. Properties of exponents. Number 19 deals with what we call the third property of exponents, when I have the same base, top and bottom, in a fraction. And I'm assuming you remember what to do. I subtract the smaller exponent from the larger, wherever the larger happens to be. The larger exponent in this case is in the top, the numerator, so it's going to be 9 minus 0. So I just get x to the 9th. Hey, another way you could think of it is x to the 0 is 1. Anything divided by 1 is just going to be the anything. So x to the 9th divided by 1, x to the 9th. All right, how about in this case? Same base. In a fractional relationship, I subtract the smaller from the larger, wherever the larger happens to be. The larger in this case happens to be in the denominator. That's where I'm going to do my subtraction. Your final answer would be 1 over a to the 3rd. Hey, in this case, notice, I got A's, I got B. I got a problem to solve here, a problem to solve there. And I think of them separately. The larger exponent for my A's is in the denominator. That's where I do my subtraction. A to the 8 minus 5. For the B's, the larger exponent is in the numerator. That's where I'm going to do my subtraction. Now I don't combine these, I don't subtract any exponents here, because notice different bases. This third property of exponents only applies when the bases are the same. So this is the final answer. All right, property of exponents. The second property of exponents we called powers to a power. When I have powers raised to a power, I multiply the outer exponent times each of the inner exponents. I could do that here, but there's a shortcut here, and I bet a lot of you see it. Look here. Anything raised to the 0 power is what? That's right, 1. Any real number to the 0 power is 1. So this just means 4 times 1. That was easy. If I did it powers to a power, I would get 4 times multiplying the 0 times each of these exponents. 4 to the 0, m to the 0, n to the 0. Remember, I'm multiplying 0 times everything. That's 0. That's 1, that's 1, that's 1. I still get 4. Either way is going to work. All right, in this instance, my question the answer to my question changes the outcome. And here's the question. What is raised to the 0 power? If you said only n, you would be correct, because 4 is raised to the first, m is raised to the first, right? So this is the only thing raised to the 0 power. That means that right there is 1. Anything to the 0 power is 1. So I get 4m times 1 is just 4m. I get 16m. So what is raised to the 0 power is affected by parentheses. All right, 2 more problems. Simplify. Notice once again I have powers to a power, except this time, I have negative exponents. I can still do it exactly the same way. I can still multiply my outer exponent by my inner exponents. And remember that 4 is 4 to the first power, right? So I got this extra factor of negative 3. I'm going to multiply negative 2 times each of these exponents. Negative 2 times 1, negative 2 times negative 2, negative 2 times 4. All right, notice what I have now. No longer have powers to a power, but what I do have that's not simplified is a negative exponent. You will never put a negative exponent in a final answer. You remember how to deal with this, I'm hoping. And that is simply make a fraction and move those factors with negative exponents to the other part of the fraction. If they're up here, move them down. If they're down here, move them up. Move them to the other part of the fraction and change the sign of my exponents. So I get negative 3, a to the 4th stays here. 4 to the negative 2, move down, becomes 4 to the positive 2. b to the negative 8, move down, becomes b to the 8th. And I typically wouldn't leave something 4 squared, so it's negative 3a to the 4th. 4 squared is 16, b to the 8th. Again, notice I don't simplify this because 2 different bases. And finally, some examples with fractional exponents. Remember our example, 8 to the 2/3? We said we can re-express a fractional exponent as a rational expression, where the base becomes the radicand, the denominator becomes the index, and the numerator becomes the exponent. So 8 to the 2/3 means the cube root of 8 squared. You got your cube root of 8 function identified on your calculator? I'm hoping so. If you can find the cube root of 8 on your calculator, you should find it to be 2. So this means the cube root of 8 squared, that's 2 squared, that's 4. So 8 to the 2/3 turns out to be 4 by translating it into a radical expression. All right, let's translate this guy into a radical expression. I know 49 is my base, it becomes my radicand. I know my denominator becomes my index, and my numerator becomes my exponent. Now I can put that exponent on the outside, or I can put it on the inside. Doesn't matter. Now I typically wouldn't write 49 to the first power, I would just write 49, right? And I typically wouldn't even put an index of 2 for a square root. That says square root right there. If there's no index, there's an understood index of 2. So square root of 49 to the first is just the square root of 49. My calculator tells me that's 7. So 49 to the 1/2 power, 7. Let's try this guy. Notice the parentheses. that tells me that everything in the parentheses is raised to the 1/2 power. It means everything in the parentheses is the base. So the new radicand is negative 49. The index again is 2, but I'm not going to put it because it's just unnecessary. The exponent again is 1. I'm not going to put it because it's unnecessary. And so I'm looking at the square root of negative 49. Now when I enter that into my calculator, I get the error concept. If I'm speaking in the realm of complex numbers, I would answer this as 7i. But if I'm just asking to simplify this, I would say no real number solution. That will be one of your options on this problem. If it gives you no real number solution, that's what you pick. Square root of a negative, no real number solution. All right, notice this guy. Hey, it's the same as that, right? Not quite. Here's the subtle difference. What's raised to the 1/2 power here? Everything in parentheses, negative 49. What's raised to the 1/2 power here? Oh yeah, just 49. So this means the negative of the square root of 49. So this negative is in essence a coefficient of negative 1. 49 is the only thing raised to the 1/2 power. Remember the definition of a base? The factor immediately or closest to the exponent, unless parentheses tell you differently. No parentheses here. So 49 is to the 1/2 power. Make it negative. Do my innermost workings first. Square root of 49 is 7. Make it negative, negative 7. Please take every opportunity to go over as many of these review problems as you can, as many times as you can. Remember, I have the neat presentation of the problem worked out on Quickly content. So run that off and have it handy for you when you take your test anywhere between Thursday morning and Sunday. Best of luck to you guys. Give me a call if you have any questions.